So yeah, hi everyone. As I mentioned, we don't really have the volunteer for today's paper, so I'll do a quick presentation instead. And today we're gonna talk about aggregate VMs. Why reduce or evict virtual machine resources when you can borrow them from other nodes? So this paper appeared at Euresys 2023. Yeah, so very recent paper. And yeah, this work was done by this amazing group of people right here. Okay, so let's kind of dive into the motivation for this paper, right? The authors claim that there is this problem of resource fragmentation in the cloud, and what they mean by resource fragmentation is there are like chunks of unused resources that exist on different servers, and these chunks are decently small, right? So they may be like too small to be used for another VM. Or like another popular VM at least. So they just like sit there unused, right? And that kind of creates the waste. Right, so they say that maybe the ideal VM placement algorithm can fix the problem, but in reality that's a very hard problem to solve. So we end up with supposedly a lot of this unused small fragmented chunks. And they also mention some like interesting details about the resource fragmentation, right? It's quite costly. So apparently, by one study, claimed that about 17% of physical resources wasted each day due to fragmentation at some cluster of some cloud, like smaller cloud provider. And like another quote that they give from Azure, given Azure's scale, even 1% fragmentation reduction can lead to cost savings in the order of $100 million per year. So, potentially a lot of money being wasted for this fragmentation, right? And the paper also says that there are some solutions for that fragmentation, like spot virtual machines or harvest virtual machines, right? So if you have this kind of unused, resources, you can sell it maybe for cheap, by allowing the creation of the spot virtual machines. So this is actually where I have a little bit of a problem with the motivation, because in my mind, spot virtual machines kind of solve a very different problem, and the same for the harvest virtual machines. And that problem is like if you can create a spot virtual machine, you have like a decently big chunk of unused resources on some server, right? So the problem that the spot VMs solve is not that we have like fragmented resources that we cannot use. The spot VM can be evicted if someone decides, well, is willing to pay for the same VM but full price. The cloud provider can evict that spot virtual machine and place the same virtual machine just at the higher cost in the same server. So, not quite fragmented, right? Like very usable resources are being like taken by the spot VMs and harvest VMs. But anyway, the fragmentation problem is what this paper is trying to solve, right? And the solution is kind of, like trivial at the very high level, right? So if we have this small unused chunks of resources that we cannot like use for anything useful, and we need to create another VM, like a bigger VM, and it doesn't fit on our servers, but maybe it can fit on more than one, right? So why not create a virtual machine that somehow spans multiple of these servers? And that's what aggregate virtual machine is, right? So it uses the resources like CPU, memory, input-output devices of multiple servers. They actually try to, make this aggregate VM fit into as few servers as possible, for performance reasons. But yeah, like it is allowed to go beyond, 1, 2, 3 servers and whatnot. And since this is a virtual machine, it is really transparent to the guest operating system, right? So you can just put your like Linux in it, and it's supposed to just work. And from the perspective of the guest operating system, it should just see all these resources from server 1, physical server 1, and physical server 2, let's say, available for its use. So the big question is like, what about the performance, right? So obviously, like if we have some CPU on server 1, some CPU resources on server 2, those two CPUs or cores are very far apart, right? So what if you need to, like, I don't know, move tasks around between the different cores, or use the memory on one core from like a physical server of another, like that belongs to another core, right? So it seems like the performance like can be really impacted if we do a lot of this, right? The authors they really claim that the performance does suffer a lot in many workloads, but they also say that there are a lot of workloads that can take advantage of this kind of extreme resource like placement in different physical servers, right? And most of this would be the embarrassingly parallel workloads, right? So something that doesn't require a lot of memory sharing. So yeah, my diagram here is kind of very simplified, right? In practice, when they have these aggregate VMs, they have the CPU, memory, and maybe like input-output devices, network cards, and whatnot of different machines all shared together, right? So like in this example, there is a 7-core virtual machine with some memory and 2 I/O devices, right? And like the figure on the left has that virtual machine spawn 3 physical servers, machine 1, machine 2, and machine 3. And then the figure on the right kind of has the same virtual machine. There's the same number of resources, the same number of cores and memory and whatnot, and I/O devices, but now all packed into just 2 servers. Supposedly, like in their work, they try to pack, as I mentioned, into like as few servers, physical servers, as possible. Again, I'm not going to go into like too much detail, so I'll make it a very like high level overview, right? But yeah, that's what they do at the high level. What enables them to do this is distributed shared memory, right? So this is not a new concept. Obviously, the paper doesn't invent this, but they use the distributed shared memory and kind of build the hypervisor on top of it, right? So the VMs, they use this distributed shared memory to provide a single kind of coherent address space to the guest OS, right? And the memory from different devices, from different servers, that is, they are mapped to different NUMA nodes, so that the guest operating system, the guest kernel, is aware that there is like different performance of trying to reach out to different chunks of memory. Right, so it is still slow, but as I mentioned, like they say that it's okay for several types of workloads. They run some experiments with different types of workloads, and they identified like few use cases, such as medium performance web servers, some function as a service infrastructure, and all kinds of like serial or embarrassingly parallel workloads, right? So anything that doesn't require to share the memory between the cores, right? So a workload that can be scheduled on the core and run on this core, all contained, like all accessing the memory that's local to that core, is the workload that's going to work the best. And this kind of notion that we don't want to share memory between the cores because the cores can be separated into different physical machines, it permeates the rest of the paper, right? So, for example, when they talk about sharing I/O devices, right? They also talk about like, well, if we expose the buffers from these I/O devices, like a ring buffer, in a distributed shared memory, that means that all of the cores that need to access the device are going to use the distributed shared memory, like the buffer in that DSM, and that's something that's going to make the virtual machine slow. So they create some workarounds for that. They use like multi-queue networking, for example, so that each core can have its own queue and its own like local memory on its own like local server, so that the sharing is minimized. So yeah, and to make all of this happen, they create a prototype hypervisor called Fragvisor. I believe it's based on KVM, so just some changes to what's already there in a Linux kernel, the biggest change is, of course, now this is a distributed hypervisor, right? So it runs on every physical machine that makes up your aggregated VM, right? So if you have, let's say, 4 servers, like here 1, 2, 3, and a little bit of here 4, 4 servers that support a particular aggregate VM, you will have the instance of Fragvisor obviously running on all of these 4 servers, and that will expose the distributed shared memory, with the networking implemented at the Fragvisor level, and all of the like other hypervisor stuff is done over the network with message passing. So yeah, I think that's probably as much detail as I want to cover for now. Yeah, let's kind of go to the evaluation. Again, the paper has quite extensive evaluation, actually. And some of that evaluation is, like, for example, about the performance of the distributed shared memory inside the virtual machine, which I kind of skipped because, again, this paper is not about DSM as much. They didn't invent that stuff. They used stuff that's available. But these figures, figure 12 and figure 13, kind of represent the use cases that they claim are acceptable for this kind of aggregate virtual machine. So figure 12 is a web serving use case. So it runs the LAMP stack. So it has Nginx, PHP, and a database and stuff like that. And what they do is they kind of simulate a PHP page rendering, right? So they run some PHP and they simulate it in terms of like how long that render takes place, how long the PHP needs to run to produce some page HTML and whatnot. And they vary this by time, so 25 milliseconds, very, very quick render, and up to like 500 milliseconds for like very slow pages and whatnot. And they compare this against a situation where the virtual machine is over-provisioned, right? So they're not comparing this against what they call the primary virtual machine, the one that is running the same number of vCPUs but on a single server. They compare this against the over-provisioned virtual machine still running on a single server, but over-provisioned virtual machine, even though it may have like, let's say 4 vCPUs, it will still run in their evaluation on 1 physical CPU core, right? So, and they try to measure the speed up over this over-provisioned virtual machine. And, in this case, right, so if you, let's look at the 4 vCPU aggregate VM, if your page render is very small, you don't get any benefit, you're actually slower. But if your page render in this case, like, yeah, even a little bit bigger, or, like what they claim around average size, 200 milliseconds, you can get up to 3 times the speed up out of having, 4 vCPUs versus like 1 physical CPU, right? So, like, to me, what this tells is, for this particular workload, aggregate VM is better than over-provisioned VM. The bottom graph is the comparison against another distributed hypervisor, but the one that's meant for kind of more HPC type workloads. And they claim that theirs is a little bit better in some cases, a little bit worse in other cases. So if you can run things for longer, if you can like keep that core busy for longer, that's where, you know, their approach, the embarrassingly parallelness of their approach, you know, shines and allows them to outperform. The figure 13 is another type of application. In this case, that's like open lambda, you know, function type workload. And we can see that, you know, for some workloads, they can get the speed up, but for some workloads, you know, even if they have more vCPUs in this aggregate VM, it's still going to be slower than this like horribly slow over-provisioned case. So yeah, I think I'm going to stop with my presentation at this point. As I said, it's going to be like very short, and we can, you know, have a discussion.